Hi, my name is Roland, and on my channel we are discussing electrical systems, solar systems, DIY builds, and from time to time we are also staying a little bit on the theoretical side, because of course I'm only a small channel. I cannot show you everything in form of a hardware here. During these videos we have to rely a little bit on paper and pens. A few weeks ago I have uploaded a video which has shown how to build up an off-grid system, simple off-grid system, inverter and a load center, and then your home installation. And about a week later, one of our most prominent YouTube channels and legendary creator in this field has uploaded a video how he has built a 48-volt solar system exactly the way like this. Very simple inverters, a load center and his appliances on it. And I must honestly say I was a little bit shocked. But you know, maybe that's only me who reacted like this, because I'm a proponent of a proper earthing system. I believe that electrical systems in the last several decades have developed to a very safe systems that there's probably very little electrical accidents, incorrectly performed installations. But so this video shall be maybe a piece of discussion. I would like to know how my viewers think about this. If somebody suggests that his electrical installation, which is not a small one, so we are talking here about 10 plus kilowatts of inverter power, and supplying a whole building or workshop with a lot of appliances, a lot of outlets where many tools or whatever can be connected and used. If this is a good idea to go for an ungrounded system. I think no. I think it's actually a very bad idea. You know that from my previous videos. I always say the first thing what I say is we have to get rid of the IT system from our point of generation when we go into a load center and start to use this in an installation. Then we want to build up a TN system of any sort, but a TN system requires a separation of neutral and PE, and we need to have the ability to detect fault currents, etc. Right, so I actually don't want to say about which channel I'm talking, about the creator which I'm talking. There's a video link on the down. If you need to see the video for the further discussion, then please go down and watch it. But if you don't want to call any names or whatever, just look my video, and this is just a case study. And once I have shown you my points of view to this, then maybe we can continue this in the comment section. So you see, when it comes to DIY home installations, inverter installations, off-grid installations, even people and professionals might get confused from time to time. And you know, it's not always that easy anyways, because if you're working with Chinese equipment, for example, those manuals are translated from Chinese into English, mostly by Google Translate and stuff like that, if in the worst case. And if you read a manual, you will sometime not know what you just read. So in this case, the builder of the system is located in the United States, and what he's building is a 48 volt off-grid system using two inverters. The inverters are the MPP solar all-in-one type inverters. Model number of that one is the LV6548. So there's two inverters which will then create two 120 volt phases, and they will then due to parallel operation and one phase shifted by 180 degrees create the split phase, right, which you have in the United States. And from the inverters he's going into a load center where he has several breakers there, and later on he will then also show how to connect, in this case it was an air conditioner, to the system. To understand the case which I will show you, we need to first define what an earthing system is and what an earthing system is for. So an earthing system is purely designed there to prevent harm for humans. So earthing systems does not have anything to do with device protection, lightning protection, stuff like that. That is a separate issue. And in case of solar systems, there you also have the surge protections and stuff like this. They're all connected to the ground as well. But I had that already in other videos on my channel. It's a different part, and it does not belong to the group of earthing systems. Earthing systems, as I said, there are several ways of doing earthing systems, and all of them are designed just to protect humans from getting electrocuted if there is some fault in the system. And there's four components in an earthing system which an earthing system needs. And the first one is the power source. The second one is the wiring. The third one are protective devices. And the last one are the appliances, the end users. And all of this is essentially the whole electrical system from A to Z, which is covered by the earthing system. Let's take a closer look to the individual components of earthing systems, and then we are going through the case. I think this time we need to talk a little bit about the IT system. The IT system is counted as one of our earthing systems, but interestingly that system comes without earthing. So that's the speciality on this. Isolated terra means the protection of this system is purely based on via isolation and insulation. So how would the IT system in the ideal case look like? This here is the ideal case. You have the power source. We only have L and N. The wires there are perfectly separated, insulated, so that usually nothing can come in contact. We have our hot and we have our appliance, and the return pass via the source neutral. There is one protective device present, and that is a overcurrent protection. So that might be an internal fuse, that might be a circuit breaker, etc. Now we need to check about appliances. Appliances are coming in insulation classes. There are four classes, class 0 to class 3. Class 0 you should actually never see. That is a completely uninsulated appliance. And a class 3 that is so over insulated that you will probably never see it. But as a consumer we will only see class 1 and class 2. And how does that look like? This here would be an appliance class 2, and this here an appliance class 1. Class 2 means the appliance is designed the way that you can never accidentally come into contact with any of the active wires here. So we have a L and a N, and that's already it. Here, usually when you have a class 2 device, you will have the symbol on it. Class 1, we don't have a symbol here, but you can see it because we have an extra PE, the protective earth wire here on this plug. So class 2 does not require earthing, class 1 requires earthing. Okay, so as I said, in the ideal case, from source to appliance, all the wires in between, everything perfectly insulated. So the risk of electric shock in a system like this is basically a zero. But in our case study, the system has been used differently. So first of all, we have our inverter. The inverter can be a IT system, or it can be then also used as a different system, as a TN system. It depends on the outside wiring, but the builder has chosen to keep it as an IT system. So the PE, even he has connected the terminal, because he has later on actually connected these two together by bonding. The PE is nothing else than a child of the neutral, so there is no protective earthing there. So just because there is a terminal screw for something on your device and you connect a wire there, if you do not follow the manual, what he did not, because the manual says that you should connect protective earth to an earthing system, to external earthing system, then there is no protective earth there. Okay, so we have the power source, the L, then of course the overcurrent protection device. In his case it was inside the load center, but of course also the inverter has overcurrent protection. And then he has connected is a class 1 appliance. So a class 1 appliance means you have a metallic chassis around your appliance, and you have a PE terminal or just wire coming out, and you need to connect this one theoretically to a earth, protective earth system. But in his case also, what he did is he used the PE and also bonded it to the neutral here. So how does this system work? The reason why this is done like this is, of course, if you have an internal fault now, as every IT system works, if you have an internal fault from L to N, or from L in this case also to PE, it will always cause a short circuit, and the idea is to trip over current, right? But that is the IT system, how it is used in our case. Okay, so this would be a simple design of an earthing system. We have our different components. We have a power source. The power source for our case study will be an off-grid inverter. It can also be the grid, it can be a generator, whatever. Then we have wiring all around. We have protective devices. When we're talking about protective devices, there's two groups. We have first breakers or fuses. So this here is a fuse. Then breakers, one pole where you only switch your L, the hot wire, and then double breakers where you switch the hot and the neutral wire. Breakers actually do not belong to the earthing protection. Breakers belong to device protection and the protection of wiring. The main purpose is, in case of short circuits, to open a circuit so that there is no fire risk because of the high currents flowing. And then the second and the most important group, because this is the group which is actually the heart of the earthing system, and this is the RCDs. In this case, a single pole RCD. This one would be a three-phase RCD. How the RCDs in United States look like, which are used in those boxes there, I don't know. This is an example for a DIN rail system. But of course, the features and the functionality is the same. And then the last component is whatever we use as an appliance on our system then. Can be devices like washing machines, air conditioners, lights, freezers, you call it, whatever the case may be. An electrical system in regard to earthing always have two separated parts. It has the normal electrical circuit, which is the hot wire and the neutral wire, and currents will flow on those active wires from the source to the appliance and then back again. And then the second part of the electrical installation is the protective installation, the protective shell around the appliances. That's the PE system, the potential earth. Everything on that circuit must have potential earth or a zero potential. As you can see, the PE is actually acting like a protective shell around our electric devices. Big appliances, devices that typically will have a metal shell, and that shell will be connected to our PE. So whenever a fault inside the device occurs, the outside shell shall always remain on zero potential. That is very important in the earthing systems. RCDs are very specialized protective devices. They have a measurement circuit inside of them. They have an input and an output. You connect input wires on one side and output wires on the other side. And the device measures current in and current out. So in an electric circuit which is 100% functional, current in must equal to current out. Whenever there is some issue in a circuit, let's say we have either a dead short from L, the PE circuit, the current will flow over the protective shell, over the PE wire, and bypass our RCD. When it's a dead short, of course, this is a high current. This would not just trip the RCD, it will also, of course, trip a breaker. But let's say that is just a leakage. So low current leakage, or because maybe our human is somehow coming in contact here to our hot wire, and because the human also stands on earth, there will be current flowing now over the human and bypassing the neutral return flow. The input current will be different than the output current. So output current will be less than the input current, and RCDs as this one here. This is a type A RCD, which is used in housing installations, and this one is tripping at leakage currents greater than 30 milliamps. So humans typically have an internal resistance as everything else. In the worst case, that might be around 300 ohms. If you have a sweaty hand and you take a firm grip on a cable, any surface which is under the high potential, so you will cause current flowing through your body which might equal somewhere around 1/10 of an amps, or maybe up to 1/4 of an amps. So that current will be missing here on the neutral because it goes somewhere around here, and this will cause the RCD to trip. So no earthing protection without an RCD. The first thing which is very important to say. Let's take a look now on our case we are talking about today. So the builder of the system is using, in his case, 2 inverters. I'm showing this here simplified with one phase inverter. It does not matter. And what he is doing is he has his load center there. He has circuit breakers inside, but he does not have an RCD. And then, what is very important, he says that what he did because his system is a pure off-grid system. His all-in-one inverters are not connected to the grid. You know, the AC in is not used. So there is no need for grounding. So he did not connect any of this to a source of ground, right? So no grounding rod, or no using of the house internal grounding system, which you also could do. First, no grounding, no PE to the system at all. And then he says that he followed the manual about bonding, and that the manual says he should bond earth and neutral inside the panel, right, in the main panel. But I've checked the manual from the LV6548 and I did not find anything about this. The only thing I found mentioned in the manual was that they say that grounding must be done via external source of ground. So what he did, he connected his 3 output terminals, L going into his circuit breakers, and neutral and ground he has put right onto the first terminal bar, while all the terminal bars, there were 3 inside his panel, all those 3 have been interconnected. So yes, neutral and ground have been bonded, but as you will see, that bond will continue within all the system. So everything else then, when he connected his air conditioner, he just took neutral and PE from the same bars there and went to the appliances. So if you look now at this setup here, forget initially this one here, what I was drawing with the human and the light fixture. We will talk about this when it comes what can happen in this system. You have your L and you have your N and PE without reference to ground. So that means that you in your setup here only have L and N, because PE does not exist, it's just parallel cabling. What is the first problem in this setup? Well, the first problem is, if you have looked other videos on my channel, we don't have a zero reference. So the bonding which you do is done because of two reasons. First, you are getting reference to zero, reference to earth into your system, integrated, right? Because in the setup like this is a IT system, as you know, an isolated earth throughout all of the system. So the neutral actually in this setup will be hot, because it is missing zero reference. So I'm pretty sure that if he measures between a point of earth and his neutral, that there will be voltage on this. What can be the problem with that? Well, look at the air conditioning circuit now. So he connected L's 1N and PE, and PE and N again ended up right next to each other on the, in this case, neutral bars we have in all of the panel now. So what you have learned before is that the PE with the appliance, with a device, a bigger device, an air conditioner like the compressor unit, does have a metal casing, now becomes a part of active neutral, right? Because it is coming from the same source. So what he has done is he has exposed one of the two active ones, and this is an absolute no-no in a housing installation. There can be now two issues with that we have exposed neutral here to the outside. The first issue, because of the missing zero reference, there could actually be voltage now on this unit from the outside. To be voltage there is now not the problem, because we don't have any connection between power source and earth. So if a human comes here and stands on the earth and touches this, there will be no currents flowing over the human. So there is a potential here, but there is no closed circuit. So it is like static electricity there, right? If you touch the unit, maybe first time you could cause a spark, but it will be no continuous current flowing over you, which could kill you, right? The second issue is that because we have exposed now one of the active wires, we only need one extra volt, which is kind of including a L, and then something really terrible can happen. So in this case, that is what I have drawn up here. Let's say we have another circuit right next to our air conditioning compressor. We have installed a light fixture. The light fixture shall have a metallic casing here, and because, you know, electricians have been lazy, same here in Thailand, they never put a earth wire to a light. So we only have neutral, we only have L, and now let's say we have a fault here, L touching the metal a fixture of the light. So just because we have put now the metal here on high potential, nothing will happen. There's no short to neutral, so the breakers cannot trip. So the light will maintain on high potential, and now is waiting for somebody to close the circuit. So now imagine that the light burned out, the light bulb, right? Our human comes there to replace the light bulb, and he's putting up a ladder here and put one foot on the ladder, the other foot on the compressor, right? Because the light is a little bit out of the way. And with his hand he's touching the light fixture. And because you know that we have exposed the neutral to the outside, we now have a L and a N, and the human is making our bridge. What will happen now? Current is flowing. The human will have a resistance, let's say around 500 to 1000 ohms. So the human will become a load for the inverter, 150 watts, if you want to say it like this. And there is nothing in the system here what will prevent electrocution. You can see current is flowing over the L, going over the human, going back over the PE to our neutral, and from the neutral back to the inverter. So the only thing the inverter will actually notice about this is that it has to output another 100 to 150 watts, and that's it. There is no protection, earth leakage protection built inside of inverter. Inverters have overcurrent protection, they have under voltage, over voltage protection, stuff like that, but there is no leakage protection there. So this is our second problem. Without an RCD we don't have leakage detection, and nothing in the world can stop you being electrocuted in this situation, other than maybe gravity if it pulls your hand away. So that's why it's absolutely important to follow the installation. Use an RCD, split up PE and working neutral, use a earthing rod, connect all other stuff with earthing which needs to be, and make your bonding wire from the PE bar to the input of the RCD neutral. This setup will cover any earthing fault, any leakage, and also most of the dead shorts by the RCD. And what is not covered by the RCD, it will be covered by the circuit breakers. Especially when it comes to us YouTube creators, to influencers, and those who have a big group of followers, you know, 100,000 views within the first 24 hours, 1,000 comments. And out from the comments you can see that most of the people are just, you know, saying, oh yeah, cool, I want to make this, I want to copy this similar as you did, because everybody can see it works, of course. But there's a big responsibility, because the copycats, there you also have to assume that they will not follow you 100% anyway. So at the end somebody can build up a system which is outright dangerous and maybe even hurt himself, and this is not what anybody wants. So that's why, please, this video is really just a case study. I want to show you this because I made other 5 videos before which have all dealt with this topic about earthing and bonding. Please, if you need to have more detailed information, look at other videos which have just more or less been released recently anyways. Okay, so I think everything is said. I want to thank you for watching this video. Please leave your comments below, subscribe to the channel, give me a thumbs up, and I see you next time.